We're surrounded by incredible tech, right?
Yeah.
Foldable phones, these health patches you stick on. It's amazing stuff.
It really is.
But there's this growing shadow, electronic waste, e-waste. Massive.
And the environment for health.
And now with all these flexible, sometimes even disposable electronics coming online, it feels like it's getting worse. Because recycling these bendy materials, it's a real headache.
Exactly. That's the problem we're digging into today. We found this fascinating research paper.
Oh, yeah?
Yeah, looking at a completely new way to handle e-waste, specifically from these flexible electronics.
Okay, what's the angle?
It's all about a new conductive ink, totally novel, made with silver flakes and, get this, a water-based polyurethane.
Water-based, like eco-friendly.
That's the idea. Super eco-friendly. Avoids all the usual nasty organic solvents.
Silver flakes and water-based polyurethane. Almost sounds too simple. So what's the big deal here? What makes this ink special for Betty the Gadgets?
Well, it's the combination of things it can do. First off, it conducts electricity really well.
Okay, essential.
Like 1.6 times 10 to the 5 Siemens per meter. Good enough for complex circuits, but it's also high-resolution printable, digitally.
Meaning precise patterns.
Exactly. And here's a really cool part. It sticks so well you can attach microchips directly. No separate glue needed.
Wait, no extra adhesive for the chips?
Nope.
That sounds like a huge simplification for making these things.
It really is. Plus, it's tough, mechanically resilient, and the headline feature, it's designed to be easily recycled.
Okay. And you mentioned attaching chips. I heard something about room temperature.
Yes, that's another big plus. The whole process, printing the circuit, integrating the chips, surface mount devices, SMDs, it all happens at room temperature.
So baking or anything?
No thermal sintering needed, which, saves a ton of energy.
Right, and lets you print on stuff that can't handle heat.
Precisely. Think paper, textiles. More sustainable substrates suddenly become viable.
Wow. And how long does this ink last? Does it need special storage?
It's pretty stable. The research showed it's good for over 4 weeks just sitting at room temperature. Doesn't really affect conductivity or printability in that time.
4 weeks is pretty decent shelf life, actually.
Yeah.
Okay, so let's walk through it. How do you go from this liquid ink to a working, flexible circuit board?
It's surprisingly straightforward, actually. You basically print the ink.
Onto what?
Onto a thin, flexible polyurethane film, like a TPU film. You can use a stencil or something called direct ink writing, basically drawing the circuit.
Okay.
Then you just let it air dry. Room temp again. Takes maybe a few minutes.
That's it? No complex steps?
For the basic circuit, yeah.
All right.
Then adding components like the chips or tiny LEDs or resistors, you place them onto the printed silver lines.
Then stick them down.
With the same ink. They call it soft soldering. You just use a tiny bit more of the silver polyurethane ink at the connection points. Let that dry too.
So the ink is the conductor and the adhesive.
Exactly. Creates the physical bond and the electrical link. All at room temperature.
Soft solder. That's clever. So these finished circuits, they can really handle being bent and twisted. I saw some pictures in the paper. Looked like they were crumpled up pretty good.
Oh, yeah. They are remarkably flexible. The research showed examples with connectors, tiny 0603 size LEDs, resistors, all still working perfectly fine, even when bent really sharply.
Wow.
Or crumpled up, or even molded onto curved surfaces. Imagine that, electronics just conforming to shapes.
Right, like wrapping around a bottle or being part of your clothes.
Exactly, that kind of thing, without breaking the connections.
Okay, flexible, easy to make at room temp.
Yeah.
Sounds great. But let's dig a little deeper. What's the science? Why does this ink perform so well?
It's about how those tiny silver flakes pack together inside the polyurethane binder. Interestingly, the conductivity actually increases slightly over the first 30 days or so after printing.
It gets better over time.
Yeah. It seems to be due to slow water evaporation from the water-based polyurethane. As the last bits of water leave, the silver flakes get packed more densely.
Closer together, easier for electricity to flow. Makes sense.
Right. It increases the silver concentration effectively. They found there's a sweet spot, though.
For the amount of silver.
Yeah. Below about 75% silver, it doesn't conduct, well, that's the percolation threshold. Above 90%, conductivity jumps up fast. But if you add too much silver, the ink gets too thick, too viscous, and you can't print it properly.
So it's a balancing act. Microscopic Jenga with silver flakes.
Kind of. Now, thinking about stretching it.
Yeah, how tough is it really? Electrically and physically?
Surprisingly tough. Electrically, you can stretch it by, say, 22 to 30% before the resistance starts to climb significantly.
Okay, so quite a bit of give.
Yeah. Electrical failure, where it stops conducting reliably, happens around 28 to 33.5% strain.
But does it snap then?
Oh, no. Physically, the material itself is way stretchier. It doesn't actually break until you stretch it like 450 to 485%.
Whoa. That's incredibly flexible.
It really is. The Young's modulus, that's a measure of stiffness, is quite low, between 10.5 and 12.8 megapascals. Very soft and pliable.
Does it bounce right back?
There's a little bit of hysteresis, meaning when you stretch it and let it go, it doesn't immediately snap back perfectly. It takes a moment to recover, but it generally maintains its function within those strain limits.
And what about those soft solder joints holding the chips? Are they the weak point?
They tested that too with resistors integrated. Those joints also showed similar strain tolerance, failing electrically around 31% stretch.
Okay.
And interestingly, if they did fail mechanically under extreme stretch, the break usually happened right at the interface between the ink and the component body. It didn't tend to peel off the underlying flexible film.
Right, so the adhesion to the substrate is really strong, okay? Tough, flexible. But the big promise was the eco-friendly part. The recycling. How easy is that, really?
This is where it gets, I think, really exciting. The recycling is incredibly simple and green.
How simple?
You literally just soak the whole circuit in isopropyl alcohol, IPA, the stuff you might have in your medicine cabinet.
Just rubbing alcohol?
Yeah, seriously. Yep. At room temperature. What happens is the IPA breaks down the water-based polyurethane binder in the ink. It basically dissolves it.
Okay.
But the underlying substrate, the TPU film, doesn't dissolve. It just swells up a bit. So the ink washes away, and you're left with the clean substrate and any rigid components, like the microchips.
Wow. So no harsh acids, no high heat?
None at all. It's a room temperature separation process using a common, relatively benign solvent.
That's fantastic. How much of the ink do they get back?
They reported recovering about 91% of the ink material this way.
Pretty good recovery.
And the TPU substrate can be cleaned and reused directly. Same for the microchips, assuming they weren't damaged. They could potentially be reused too.
And the silver in the dissolved ink?
You wash the recovered silver flakes with more IPA. That gets rid of the dissolved polyurethane residue.
Do you lose much silver doing that?
There's about a 20% loss of the ink material during that washing step to purify the silver. But the recovered silver itself can then be used to make new ink.
And is the recycled ink any good?
Remarkably good. Its conductivity was only slightly lower than the original ink, like a 2.4% decrease.
That's barely anything. Any downsides?
It did lose some of its stretchability after recycling, so maybe not quite as robust for extreme bending applications the second time around, but still very functional.
Still, that sounds way better than current recycling methods or lack thereof. And the substrate, the flexible film.
The IPA treatment didn't seem to affect its mechanical properties, so you could genuinely reuse it in a new device. It points towards a truly circular process.
A circular life cycle for flexible electronics. That's the dream, isn't it? Now, I saw they also mentioned adding liquid metal to make it even stretchier.
Ah, yes, the e-gain, eutectic gallium indium. They experimented with adding that to the silver polyurethane ink.
Why?
To really push the stretchiness. With the liquid metal added, it became a sort of biphasic compound, and the stretch tolerance before electrical failure shot up dramatically.
How much?
Over 200% strain, compared to maybe 30% without it.
That's a huge difference. How does the liquid metal help?
The idea is that the liquid metal forms these continuous conductive pathways that can deform and stretch, kind of bridging gaps that might form between the silver flakes at very high strains. It helps stabilize the network.
Does it hurt the initial conductivity?
Not significantly, no. The initial conductivity was pretty similar.
Well, it's always a but.
There's a but. Recycling gets trickier.
Ah, why?
Because the gallium and indium in the liquid metal can actually alloy or mix with the silver flakes at a metallic level. Separating them back out is much more complex than just washing away polyurethane.
Okay, so extreme stretch comes at the cost of easy recycling. A trade-off.
Exactly. So for the applications they focused on demonstrating where recyclability was key, they stuck with the original AG-WPU ink, no liquid metal.
Makes sense. And what were those applications? Where could we actually see this ink being used soon? They mentioned smart packaging.
Yeah, this is where you see the real-world potential. They built a recyclable smart label for monitoring food temperature.
Like on a milk carton.
Exactly. Or they showed it on a fish package and integrated into a water bottle. It had tiny LEDs that would light up based on time and temperature thresholds.
So it tells you if your food got too warm for too long.
Precisely. Indicates if it might be unsafe. It even had Bluetooth Low Energy BLE connectivity.
What for?
So you could potentially check a historical log of the temperature exposure on your phone.
That's brilliant. And the whole thing, label and package, is recyclable.
That's the key point. The packaging itself uses conventional recycling, and the smart label part uses the new IPA process. Fully recyclable system.
No more sniffing the milk uncertainly.
Oh.
But what about the health monitoring side?
Also very promising, they made several types of wearable patches.
Like sticking plasters with electronics.
Sort of, yeah. One was a straightforward body temperature monitor, printed onto a patch placed under the arm.
And did it work?
Yeah, gave readings that matched up well with a commercial thermometer, continuous monitoring, potentially.
Okay, well, what else?
They also made a more complex patch with multiple electrodes for electrophysiology.
Recording body signals, like muscle activity.
Exactly. They showed it recording EMG signals from forearm muscles. You could see different signal patterns when someone made a fist, moved fingers, or varied their grip strength.
Wow. Could it do other things?
They even used it for facial expression recognition. Put the patch on the face and it could pick up repeatable signals for smiling, frowning, etc.
Huh. And heart monitoring, too.
Yep, demonstrated a single lead ECG setup, showed clear PQRST waves, the standard ECG features, and gave a reasonable heart rate measurement.
That's quite a range from just printing ink on a flexible film. Did they compare these printed electrodes to the usual sticky gel ones you get at the hospital?
Yeah.
The EGACL ones?
They did. The printed ones actually had lower intrinsic resistance, meaning the material itself conducted better.
Right.
But they had a higher interface resistance when put on the skin. Skin contact wasn't quite as perfectly conductive as with the wet gel.
So pros and cons.
Right. But the printed dry electrodes have big advantages too. Much easier and cheaper to fabricate, you can customize the shapes easily, and maybe less signal degradation or crosstalk over long periods compared to gels drying out.
Okay, so stepping back and looking at the big picture here, we've got this new electronic ink.
Right.
It's conductive, printable, acts as its own adhesive for chips, works at room temperature, it's flexible.
And critically, it's designed for simple, eco-friendly recycling using just IPA.
It really feels like it ties together a lot of desirable properties that other approaches haven't quite managed all at once.
That feels like the core aha moment here, doesn't it? It's this combination, relatively simple materials, straightforward, low-energy processing, high functionality, and a clear path to a circular life cycle. That's often been the missing piece for soft, flexible electronics.
It really does. It makes you start thinking, what does this enable? If we can make flexible, functional electronics that aren't an environmental nightmare.
Exactly. The implications are significant.
Could this dramatically reduce the e-waste mountain? Could disposable electronics actually become truly sustainable? What else could you do with this? Smart bandages, even more integrated wearables, packaging that does more than just contain.
It opens up a lot of questions, doesn't it? How could this kind of approach fundamentally change how we design, use, and crucially dispose of electronics in our daily lives, moving towards something much more sustainable?
Definitely food for thought. If you, listening, want to dive deeper into the nitty-gritty technical details.
Yeah, the original research paper is the place to go. It's packed with data on the material science, the fabrication, the testing.
It really shows the work behind developing this recyclable thin film tech and gives you a much richer picture of where sustainable electronics might be heading. Definitely worth a look.